on the rank series and the complex and the method of integration. I would like to mention global Cauchy theorem. So I decided to add a section in chapter 14. The subject is about global Cauchy theorem. Right. All right. So before we state global Cauchy theorem, we need several new concepts. All right. So we first denote a formal sum. Okay, gamma equal to eta gamma 1 plus dot plus gamma 2 dot plus is up to dot plus gamma n, okay, as a chain consisting of n passes, okay, gamma I from 1 to up to n, okay, and we define the line integral of a complex function f sub z of z over the chain gamma as the following. Okay. So this is the line integral of the complex function f of z over the chain gamma, and this is defined to be the summation of the line integral of the same complex function f of z over the ith path, okay, and sum over all the I from 1 to n. Okay, so this is the definition for that. And provided that each line integral gamma I f of z dz of f of z over the ith path gamma I exists, okay, for I from 1 to up to n. Okay. All right. So the purpose to define a chain of passes in reality is to define such a line integral over a chain gamma. Okay, so that's it's just the finite sum there. And if each gamma I is a closed path, okay, then a chain gamma is called a cycle. So a cycle is a special kind of chain such that each component passes a closed path. Okay. Any questions about the definition? Now a chain may be represented as a sum as a formal sum of passes in many ways. Okay, right, and so to say that two chains are equal, so here it's, so the first here is a chain of n passes is equal to the other chain of passes of n passes. Okay, we say that these two chains are equal. We mean simply that the summation okay, we mean that okay, so the line indigo over the chain, the left chain, by definition, which is equal to the line indigo over the left chain. Okay, for every complex function f of z which is continuous which is continuous on gamma 1 star union gamma 2 star union union gamma n star union delta 1 star union delta 2 star union union delta m star. Okay. Because when the complex function f of z is continuous on this set, right? This set in the complex plane, then every line integral, right? Every line integral exists and has finite value. Okay, so that. Okay. So we use the equality of the value of line integrals, right, to define the equality of two chains. Okay, so we have okay, these two chains are equal means that the equality always holds for all complex functions. So this is true for all complex functions which is continuous. Okay. All right, and so in particular, a cycle may very well be represented as a formal sum of passes that are not closed. Okay. All right. So now we define gamma star. Okay. So define the range of a chain gamma, which is just the union of the component, the range of each component path. Okay. Right. So we define this one. Okay. And so a chain gamma is said to be in a set E in a subset E of the complex plane if gamma star is contained in E. Okay. All right. Now, if gamma is a cycle, okay, so a cycle is just a chain of closed passes, and Z sub 0 is not in the range of the chain gamma star. Then the index Z sub 0, the index of Z sub 0 with respect to the chain gamma is defined as here. So the index of Z sub 0 with respect to gamma is defined to be 1 over 2 pi I of the line integral of over the cycle gamma of this complex function. Okay, this complex function. And by definition, this is just equal to summation from 1 to n. Okay, and 1 over 2 pi I over the gamma I over z minus z0 dz. So this becomes to be the index of Z sub 0 over gamma I. Okay. Okay. So this is a very straightforward definition. Okay. So where gamma, the cycle gamma is the chain of n cross passes. Now we define the reverse of the chain gamma. So define this is to be. So we reverse the direction of each component path. Okay, so it's minus gamma 1, minus gamma 2, that minus gamma n. Okay. Right. So we define minus gamma to be this chain. Okay. Now with this definition, so we have in the range of the reverse gamma is actually equal to the range of the gamma itself. Okay, and we know the line integral of minus gamma, which by definition is equal to minus gamma I fz dz. And we know the line integral of f of z over minus gamma is equal to the minus of the line integral of f of z over gamma I, as we have discussed in chapter 14. Okay, and so this becomes to be minus gamma fz dz. Okay, so for every complex function f of z, which is continuous on gamma star. Okay, and in particular, we have here the index of z over minus gamma is equal to the minus of the index of z over gamma here. Okay, if gamma is a cycle and z is not in the range of the cycle gamma. Okay, so they are about the chains. Now chains can be added or subtracted, right, in the obvious way. All right, so for example, the sum of two chains. So the sum here, the dot plus, okay? So the sum of two chains, again, is a chain, right? And so you can see this is, right? So the line integral of a complex function of the sum of two chains is equal to the sum of the line integrals, okay, of fz over gamma 1 and over gamma 2. Okay, so this is the, and minus gamma 2, the subtraction. So this is actually the gamma dot plus minus gamma 2. So this is the difference. So this is equal to the difference of these two line integrals. All right. So this is for every complex function. Okay. F of z, which is continuous on the set gamma 1 star union gamma 2 star. Okay, now we are able to state the global Cauchy's theorem. Alright, so we let f of z be analytic in an open set omega in the complex plane. Okay. Right. And if gamma is a cycle in omega, which means that the range of the cycle is a subset of the open set omega. Okay. Right. So if gamma is a cycle in omega such that the index of point z over gamma is 0 for all z not in omega. Okay. Right? So suppose we know this data. Okay. Then we have the Cauchy integral formula. So fz times the index of z over gamma, restricted to gamma, is equal to 1 over 2 pi I of the line integral over the cycle gamma of this function for all z in omega, but without point, okay, in the range of the cycle gamma. Okay. Okay. So this is a very strong result because this is true for any cycle gamma in the open set and the omega just an open set. Okay. So this is the Cauchy integral formula we have. Okay. And also we have the Cauchy integral theorem, which says that the line integral of the analytic function f of z over the cycle gamma is equal to 0. Okay? But this is a very strong result. Okay? And the only requirement is that we have to know the index of all points outside the open set must be 0. Okay, with respect to the cycle, must be 0. Okay? All right, and if gamma 1, if we have two cycle, okay, in omega, such that the index of z, right, over respect to gamma 1 is equal to the index of z with respect to gamma 2 are equal for all z not in omega. Okay, so if then then the line integral of the analytical function f z over gamma 1 will be equal to the line integral of f of z over gamma 2. Okay. Right. So we have two results, and this theorem is called the global quantity theorem. Yeah, because it's valid for any open set omega. Right? Any open set omega, and every cycle in omega. Okay, and the only for the first part has the requirement that the index of any point outside the open set must be 0 with respect to the cycle gamma. So this is important. It's important. So once we have this result, then we have the Cauchy's integral formula here. Okay, for every z, right, in the open set, but cannot be on the range of the cycle gamma, and also we have the Cauchy integral theorem that this integral of the analytical function f of z, okay, over gamma is equal to 0. Right? So this is the first part. The second part is that if we deal with two cycles, gamma 1 and gamma 2, in the open set, such that we know that with respect to gamma 1 and with respect to gamma 2, any points outside of the open set omega has the same index. Okay? So if we have this data here, then these two line integrals must be equal. Okay? Right? So it depends on the required data. You have different conclusion here. Okay? So this is a very general settings we have. The Cauchy's integral theorem as well as Cauchy integral formula we proved before in chapter 14. They are all usually local properties. Okay, and so either the open set is specialized. For example, the omega may be just an open convex set. Okay, and the cycle is just a closed path. Okay. Over omega is an open set, but the cycle is just the boundary of a triangle. Right? So they have restrictions. Right? They have restrictions, and so they usually call the local Cauchy theorems. Right? And so this is the most general Cauchy theorem we can have. Right? So we will use this global Cauchy theorem in the discussion of chapter 16. Any questions? So I am currently writing down a proof of this global Cauchy theorems for you. Okay, this is the reason why I haven't sent the lecture notes of chapter 14 to you. Any questions? Okay, so if no questions, then I will start with chapter 16. Okay, so we'll talk about Lorentz series and rate integration. Rate integration is a very special kind of method to deal with complex integration, right? And so this is very useful. All right, so we first discuss a Lorentz series. All right, so now given, so we have defined power series. So a power series is defined by a given sequence of coefficients, okay? And A0, A1, A2, so the sequence is one side, okay? And a center Z0, right? So that a formal power series can be defined by a sequence of complex numbers and a center Z sub 0. And similar, we will give the definition of the Lorentz series in a similar way. All right, so given a complex number Z sub 0 and a so-called two-sided infinite sequence so it's Cn, but n is from minus infinity to infinity. So the n spread to minus infinity as well as past infinity. Okay, so it's called a two-sided infinite sequence of complex numbers. Right? Then the two-sided infinite series of power function. Okay, so this is n is from minus infinity to infinity, and Cn z minus z0 as power. Okay, so this two-sided infinite series of power functions is called Lorentz series. All right, about z equal to z0, where z0 is called the center. And Cn, the coefficients of the Lorentz series okay, and if we without explicitly mentioning the center, a Lorentz series, okay, will be assumed to have 0 as its center. So that is a convention. Okay. All right. So So this is the a two-sided infinite series of power functions. So each term is a power function. If we assign a value to the variable z here, so if suppose z is assigned to a value, then this is become to a two-sided series, okay, of complex functions. And this is two-sided infinite series may converge or may not converge. Okay, so we have to justify conditions of convergence. Right, so here we give the first theorem. So given a Lorentz series and from -infinity to infinity, Cn z minus z0 to n's power, we let alpha to be the lim sup, okay, of the nth root of the s value of the coefficient with positive index n. Okay, so in here, so alpha is this sequence when n goes to infinity. And we have a beta. So beta is the lim sup as n goes to infinity of the nth root of what? Of the s value of c sub n minus n. So as n goes to infinity, the minus n goes to minus infinity. Okay, so that beta is just the upper limit of the nth root of the s value of the coefficients with negative power. Okay, so negative powers. Okay, we have two directions. So this is positive directions. We have upper limit, and for the negative directions, we have the another upper limit here. And as we discussed in chapter 15, these two upper limits must exist. Okay, must exist. And of course, because that you see that this number is always non-negative, so these two upper limits must be greater than or equal to 0 and less than or equal to positive infinity. Okay. All right, so if we have to find out the alpha and the data, then the Lorentz series converges absolutely if the difference has absolute value greater than beta but less than 1 over alpha. Okay. So if we have that and diverges, if either z minus z0, either the distance between z and the z0 is greater than 1 alpha, or the distance is less than beta. Okay. So alpha and beta are two very important numbers to determine, right? So that we will be able to state the convergence or divergence conclusion. Right, and so let's see a proof. Okay. Now for each choices, so each choice of Z in the complex planes, the infinite series summation Cn Z minus Z0 and power. Okay, look at here. The index and the power and start from 0 to infinity. Okay, so we look at the positive side. All right, because the original series is two-sided, so we partition a two-sided series into two parts. One is the right-sided or the positive sided. Okay, so the infinite series. So if we choose a value, right, for Z, then this becomes to a numerical infinite series. Okay, and this series converges. Okay, absolutely. If the lim sup n goes to infinity of the nth root of the nth term. Okay, if this one is this one, and the diverge okay, if the lim sup, if this lim sup is greater than 1, okay. All right, so this is by the root test. Okay, by root test in theorem 15.1.0. Okay. Also, the infinite series summation n from 1 to infinity C minus n, Z minus Z0 minus n. So you see this is the infinite series associated with the negative side. Okay. So this one converges absolutely if the lim sup of the coefficient minus n, okay, C sub minus n, and the power is also minus n as n goes to infinity. And so this lim sup should less than 1. So if this lim sup less than 1, then the infinite series, because we have select the value of Z already, so we have assigned Z by a value. Okay, and so this is come to a numerical infinite series. Right, so the infinite series and diverges, okay, if the lim sup is greater than 1. Okay. All right, so this is again by the root test in theorem 15.1.0 here. Okay, now right, as we discussed in section 15.2, okay, so this condition, this one is equivalent to that so that z minus z0 as s value, okay, less than 1 over lim sup. Okay, and here, okay. All right, and also this is going to say that z minus z0 is greater than 1 over the lim sup. Okay. Okay, and for this one, so this, okay, so this one is equivalent to here, that's the lim sup c minus n, this then z minus z0 here, because this is minus n. Okay, so we have here, and in this condition, okay, goes to lim sup c minus n, less than greater than this. All right, this one goes in z minus z0. Okay, so we have, okay, so now the Lorentz series summation converges absolutely, okay, if this, so if both from 0 and summation from 1 to infinity c minus n, okay, if both converge absolutely. Alright, so if and only if, okay, converging condition is not. So if both converge absolutely, i.e., and we know here so that's if so we have two conditions to check. One is that this must be true, this is true. So z minus z0, that's then 1 over the dim sup okay, and should, right? And the difference should greater than this dim sup. Here. All right, so if Z satisfy these inequalities, then the Lorentz series converges absolutely. Okay, and we know this lim sup, this is equal to beta by definition, and this one, the denominator is defined to be alpha. Okay. Okay. So we have the first result. So if the distance z from the center z sub 0 is in between beta and 1 over alpha, then the Lorentz series converges absolutely. Okay. And so the Lorentz series diverges, okay, and the Lorentz series diverges if either the positive part, okay, if either this diverges over the negative part diverges. Okay. Right. And from here, if this lim sup is greater than 1, then the positive part diverges. So if either okay, so if either z sub the distance z from z0 is greater than 1 over alpha, okay, so we define the denominator is alpha, or z sub z0 here less than beta here, then Lorentz series diverges. Okay. Right, so this is the end of the proof. Any questions? All right, so we have some remarks. If the beta is greater than 1 over alpha, right? So if beta is greater than 1 over alpha, you see that all right, then one of these two conditions, then either z minus z0 greater than 1 over alpha, or z minus z0 less than beta. Okay, so that the Lorentz series diverges for all z in the complex plane. Okay, so the Lorentz will diverges. Why? Because as we know, so suppose beta is greater than 1 over alpha, okay? So we have here. So suppose this is 1 over alpha. And then we have, so here this is beta. Okay. Now, we know if the distance is greater than 1 over alpha, so if the distance is here, okay. So this part is z sub 0. Z minus z sub 0 is greater than 1 over alpha. And here, okay, here is z sub minus 0 is less than beta. Okay. So the union of these two colors, the shaded region, is the whole complex plane. Okay. So that's why, so if beta is greater than 1 over alpha, then either z is greater than 1 over alpha or z is less than beta. Okay, oh, I see. I have to say here is z sub 0, okay? Okay, so beta, so if beta, this beta is greater than 1 over alpha, then the Lorentz series diverges everywhere. Okay. Second part, if beta is less than 1 over alpha, then the Lorentz series times power converges absolutely in the open annulus A Z sub 0 beta and 1 over alpha. Okay, the open annulus is actually the domain such that okay, so it will be in the open annulus. So it's here. So suppose that G sub 0 this is beta, and the other is 1 over alpha. So if beta is less than 1 over alpha in the shaded region, so the open annulus will be this region, which is the domain. Okay, so it's an, you can see it's an annulus, right? And this is an annulus. Okay, so the rank series okay, well, converges absolute in the open annulus, and but in here it diverges, and also in the inner of the inner circle, inside the inner circle, that every point inside inner circle also diverged, and any point outside the outer circle it also diverges. Okay. Okay, and the Lorentz series right diverges. Okay, diverges outside the closed annulus. We call A bar Z0 beta and 1 over gamma. And the closed annulus is just the open annulus plus the two boundary circles. So this is the point such that less than equal to Z minus Z0 less than equal to 1 over alpha. Okay, this is called the closed open annulus A bar here. Okay, and the open annulus here, the open annulus here, so this one is called the convergence open annulus of the Lorentz series. Summation n from -infinity to infinity. Okay. So unlike a power series, as we discussed in chapter 15, a power series has a convergent open disk. Okay, open disk there. And but for the Lorentz series, there is a unique open convergent open annulus. Okay, a unique one. All right, and so that's in between beta and 1/alpha here. Okay, and then you have to know how to compute alpha and beta. Any questions? Okay. The property, a power series is a special type of the Lorentz series. With c minus n equal to 0 for all n. Okay, so you can regard a power series as a special type of Lorentz series, and the coefficients of the negative power terms are all zeros. Okay, so in this case, the beta itself is the lim sup of 0, right? But the 0 sequence has limit already, so the upper limit also 0. Okay. All right. So that's the convergent open annulus of the power series and from 0 to infinity x here, x annulus of z0 and the 0 1/alpha with alpha equal to lim sup of the nth root of the absolute value of the coefficients of positive power terms. Okay, so we have that. But since the power series always converges to 0 when z equals 0. Okay? Then thus then on the disk or the open disk, which is just the open annulus over R union the center. Okay. So the open disk is actually the union of the open annulus plus the center Z0. Okay. So this one becomes to be the convergence disk, open disk. Of the power series. Okay. Right. So you can see that the Lorentz series, concept of Lorentz series, is an extension of the concept of power series. Okay. So it's more general. Okay. Any questions? So if no question, then we take a break up to 2:45. Okay. In chapter 15, we consider a power series, and we know we can define a function by given a power series on its convergence open disk. So we can do this, the same thing that so for a complex with a center Z0 and coefficients Cn, we can define a complex function on the open annulus A Z sub 0 beta and 1 over alpha as here. So we can define okay, provided that the beta, which is the lim sup is less than 1 over alpha, which is equal to okay. So we can define a complex function by a Lorentz series for all the variable z in the convergent open annulus. Okay. All right, so we should say that the complex function okay, f of z is given by a Lorentz series okay, about the point z equal to z sub 0. All right, now so we have a similar theorem to theorem 15.3.8, because in theorem 15.3.8 give property of functions given by a power series. Now we have a function given by a Lorentz series. Okay. So if a complex function f of z is given by a Lorentz series about the point z equal to z0 with convergent open annulus A z0 beta 1 over alpha. So f of z is defined in this way. Okay, so if a complex is given by a Lorentz series, then this then f of z is analytic in the open universe and its derivative f prime z can also be given, okay, by a Lorentz series about the same point z equal to z0 with the same convergent open annulus A z0 beta 1 over alpha, which is obtained by directly differentiating each term of the original series, i.e. f prime z actually is equal to n of Cn and z minus z0 minus 1, okay, for all z in the open annulus. Okay. Okay. So if a function is given by a Lorentz series, which defined in the convergent open annulus of the Lorentz series, will be analytic. Okay. In the defining open annulus, and its derivative, okay, its derivative can also be given by a Lorentz series, right, with the same convergent open annulus, okay, the same, and this Lorentz series is obtained by termwise differentiation, okay, by termwise differentiation. So that is very nice to have this property. Okay, so I will sketch a proof, okay, because a large part of this proof will be the same, will be very similar to, not the same, similar to the proof of theorem 15.3.8, okay, we discussed before. Okay. So we note that Okay. So first of all, we will show that this new Lorentz series by termwise differentiation, okay, has the same convergent open annulus as the original one. Okay. Right, so the Lorentz series obtained by termwise differentiation of the original Lorentz series X here and Cn z minus z0 and minus 1. Okay, so we can rewrite. So by reindexing, we have n plus 1 and c sub n plus 1, z minus z0 n's power here. Okay, so now that is the terms of n's power. And then we split, right, this two-sided series into sum of one-sided series. The first one is the positive-sided, plus summation, right? So now we have from n equal to 2 minus n minus 1, c minus n minus 1, and z minus zn, z sub 0 minus n. Okay, so we just write the two sum by a standard form. Okay, so that this is the mass and power term here, and the coefficient will be this one. Okay, and we start from n equal to 2. Yeah. All right, and this Lorentz series has the same convergent open annulus A, Z0, beta, and 1 over alpha as the original one. The reason is here. If we consider lim sup, n goes to infinity, and this is n plus 1, Cn plus 1. Okay? And we deal with this part. Okay, so we know this is ER equal to the lim sup of the original sequence, which is alpha. All right, so this one, as shown in the proof of theorem 15.3.8. Okay, and so this part, so we're here for this positive even series. Okay, the lim sup of the corresponding coefficients here will be the same as the original one. So it is alpha. Okay, so we have done this before, so we do not need to repeat here. And we look at lim sup, all right, of the negative-sided unit series. So that would be S value here. Okay, so look at the coefficients. All right, and of course we can proceed the similar procedure we took in the proof of theorem 15.3.8. So that this is the lim sup and goes to infinity. So we use the exponential function of the natural logarithm. Okay, and this is n minus 1. C minus n minus 1. Yeah. And because exponential function is multi-increasing continuous function, so that we will move the lim sup to the exponent term. Okay. Okay, and all right, and so we deal with the exponent term. Now the lim sup so this is and here plus the lim sup okay. All right, now the sequence, the first sequence has a limit and go to 0. Okay, so of course that the lim sup will be equal to the limit. So this is equal to 0 plus the lim sup. And here we consider okay, times this one. Now the first sequence goes to 1, so has limit goes to 1. So this is goes to limit and goes to infinity and n minus 1n. Okay, this one times the lim sup. Minus 1. Okay. So this is by theorem 15.1.I, I think so. Okay. And the first limit is equal to 1. So this is equal to, and by change of variable of index, so this is goes to infinity n and okay, here. So we have here, and this is the lim sup. Look n. Okay. So this lim sup of this equal to the lim sup of this one. Okay. Now we take the exponential function back. Okay, so that lim sup becomes to the exponential function of the lim sup okay, and this is the lim sup exponential function. Okay, and this is the lim sup and which is just equal to beta. Okay. Okay, so the new Lorentz series by termwise differentiation of the original Lorentz series will have the same convergent open annulus. Okay. Okay, and so we define. So we define the G of Z. Okay. All right. It's the complex function given this new Lorentz series. Okay, so we define this complex function. We define this complex function here. Okay. Okay, and also, so now we should show that G of Z is actually the derivative of f of Z, okay, before. So we fix W, okay, in the open annulus, and we choose, okay, R1, R2 greater than equal to 0, such that beta is less than R1, and the point, okay, so that because W is in the open annulus, okay, so there is some distance. But because the distance must be in between beta and 1 over alpha, so we can select R1 and R2, okay, in between there. Okay. So now if Z is not equal to W, so we have here, so we want to show now the quotient divided by Z minus W. Okay. So we want to show that when Z goes to W, this quotient goes to GW. Okay. So we evaluate the differences. Okay. And we can show that the difference, okay, can be upper bounded by Z minus W with something which is n squared Cn r 2 n minus 2 plus n equal to 1 infinity n squared C minus n absolute value R1 minus n plus 2. Okay. Okay. So we have, by a procedure, similar to that in the proof. of theorem 15.3.8. Okay, so please see the lecture notes. So I will send you a lecture note for the detail. Okay. All right. Okay. I see. If you remember the procedure we take in the proof of theorem 15.3.8 is lengthy, right? Actually, I have do some algebraic manipulations. Even though these algebraic manipulations are simple, but it takes time. Okay, so because the idea will be similar, so I will omit the procedure here. And so, but I will write the detail in my lecture notes for you to read. Okay, so anyway, we have this one. Okay, and as we know that the R2 here, you see the R2, right? So because R2 is less than 1 over alpha, so that this sequence will converge. Okay, let me address that. Right, since we know beta is less than R1, less than R2, less than 1 over alpha. So we have, so let's see why this sequence converge. We can use the root test again, right? So we have here the lim sup of n goes to infinity, and n square, the nth root of the absolute value of the terms here. So this is Cn, and the R2 and minus 2 here. Okay, and so this is R2 lim sup n goes to infinity. Okay, and the square. Okay, and Cn here. Okay, but the sequence of n, the nth root of n goes to 1. As n goes to infinity, we know this sequence converge to 1. Okay, so that this is equal to R2 and the lim sup of n Cn, since the limit n goes to infinity equal to 1. Okay, this is a famous sequence we have in calculus. So if but and we know this limit. We know this limit is equal to alpha. Okay. So as you see that when you multiply alpha here, so this is less than 1. This is less than 1. Okay. So by root test, the lim sup, by root test, so this sequence converges, and we see the convergence property of the second series. So this is n square, C minus n, and R1 minus n plus 2. Okay, so this is 1 over R1, and the lim sup n goes to infinity, n square, and here. Okay, and so this is 1 of 1, and this is the dim soup, and goes to infinity. Sinks again, the limit of n goes to infinity, and equal to 1. And so this is beta divided by R1. But when we divide R1 here, we know this is less than 1, too. Okay, so by root test and by root test, okay, by root test that the two-sided infinite series I think I have to make a correction in my notes. Okay, so that this term by summation okay, right, has a finite sum. Okay, so this has a finite sum. Now, as C goes to W, you can see this quotient goes to GW. So as Z goes to W, then the quotient goes to GW. Okay. Which shows that f of Z is differentiable at Z equal to W, and f prime W is equal to G of W for all W in the open universe. Okay, and which is done. So we complete the proof here. Okay. All right. So a complex function given by a range series has similar length property as a complex function given by a power series. Okay, because both of them are analytic functions, and their derivatives is actually equal to a function given by a range series by termwise differentiation of the original Lorentz series. Okay, so that is a nice property we have. Okay, all right. So I stop here. Okay, and we will continue discussion on Thursday. Okay, so once I have done the writing of section 14.5, which is about global Cauchy theorem, then I will send you the lecture notes of chapter 14.